Welcome to our quantum deep dive. Today we're plunging into a truly, well, remarkable corner of quantum physics, positronium. It's this exotic system that, beautifully blurs the lines between what we call matter and antimatter. And as we'll discover, it holds some incredible secrets about the universe. Our guide for this journey, drawing from his insightful essay, is Jurgo Schneppe.
Yeah, it's fascinating stuff. Positronium, often just called PS, it's transient. It doesn't last long, but it's profoundly important. Imagine an electron basically dancing with its antimatter counterpart, a positron, just for a moment. It really is a fantastic natural laboratory, not just for testing fundamental laws, but for giving us these unique aha moments about quantum electrodynamics and the very nature of symmetry in our universe.
Right, like a mini atom, but with this really surprising twist that kind of redefines what an atom can even be. We'll unpack its unique properties, explore how scientists actually create and detect this fleeting thing, and uncover its surprising applications. From scanning for tiny defects in materials all the way to potentially powering future quantum technologies. So, to kick things off, what exactly is positronium, and how does it stack up against something we know better, like, say, a hydrogen atom?
Okay, so at its core, positronium is indeed a bound state. You've got an electron and a positron held together by the electromagnetic force. Functionally, yeah, it's quite similar to a hydrogen atom, electron orbiting a proton. But, and this is key, the differences are crucial. They really define its exotic nature.
Okay, let's unpack that. We're talking an electron and an anti-electron, so there's no heavy nucleus like the proton in hydrogen. How does that change things?
Precisely. That lack of a massive nucleus means two really significant things. First, its reduced mass is only half that of a hydrogen atom, specifically half the electron's mass. This basically means positronium behaves like a much, much lighter atom. It significantly impacts its energy levels.
Lighter.
Second, because both particles have the same mass, there's no central heavy anchor point like in hydrogen. Its energy, eigenvalues, those specific allowed energy levels for the system, follow a modified Rydberg formula. And these energy levels turn out to be exactly half as large as those of hydrogen. So for instance, its ground state binding energy is only 6.8 electron volts compared to hydrogen's 13.6 eV. It's just less tightly bound.
Right, so it's lighter and less tightly bound. That makes sense. But the thing that really jumps out at me is its lifespan. Hydrogen is stable forever, basically. Positronium sounds incredibly fragile. How challenging does that make studying it?
You've hit on something absolutely crucial there. While hydrogen atoms stick around, positronium is, well, incredibly short-lived. It decays through electron-positron annihilation. Its entire mass transforms into pure energy, specifically photons.
Photons, right, light.
Exactly. And these photons are really distinctive. Each carries 511 keV of energy, which is precisely the energy equivalent of an electron's mass, or a positron's mass. It's a perfect, direct demonstration of EMC in action. This rapid annihilation gives it a lifespan ranging from about 10 to 10 to 7 seconds. It depends on its quantum state.
Wow.
Yeah, it's a blink of an eye in our world, absolutely. But in the quantum realm, that's actually a measurable lifetime for doing some really cutting-edge research.
So we've got this extraordinary fleeting system, lives for less than a billionth of a second. How does it even come into existence? And more quickly, how does this incredibly rapid dance between matter and antimatter actually end?
Right, so positronium forms when a positron, the electron's antiparticle, bumps into an electron, either a free one or a one bound inside an atom. This can happen in a few ways. It can be a byproduct of beta decay in certain radioactive isotopes. It can be created in high-energy collisions in particle accelerators, or, quite commonly in experiments, when you inject positrons into certain materials. Formation is most likely when the particles don't have much kinetic energy. Low energy allows the Coulomb attraction, the electromagnetic pull, to actually bind them together into this temporary atom.
Okay, but it's not just one simple type of positronium, right? I heard there are distinct personalities, maybe spin states, that behave really differently, especially how long they last.
That's a great way to put it, yeah. There are two main spin states, and they each have a very different fate. First, you've got parapositronium, or PPS. This is the singlet state. The electron and positron spins are anti-parallel. Think of them like tiny magnets pointing in opposite directions. The total spin adds up to 0. S-Rhombus. This state decays primarily into two of those characteristic 5 out of 11 keV photons shooting off back-to-back in opposite directions, and its lifetime is incredibly short, about 1.25 times 10 seconds. Really fast.
Okay, that's para. What's the other one?
Then there's orthopositronium, or OBSE.
Yeah.
This is the triplet state. Here, the spins are parallel pointing in the same direction, so the total spin is S1. Now, here's where it gets really interesting. Because of a strict quantum rule, something called parity conservation, like a cosmic gatekeeper,
Uh-huh.
it actually cannot decay directly into just two photons. This forces it to decay predominantly to three photons instead.
Mm.
And this three-photon process is much slower. It gives OPS a significantly longer lifespan, around 1.4 times 10 to 7 seconds.
Wow, that's like 1,000 times longer.
Roughly, yeah. About 1,000 times longer than PPs. And these differences, the lifetimes, the number of photons, they're all precisely predicted by quantum electrodynamics, QED, our best theory for this stuff.
So just a tiny difference in spin, how they're aligned, leads to this massive difference in decay and lifespan. But capturing signals from something that vanishes in, billionths or even 10 billionths of a second, that seems like a monumental challenge.
Yeah.
How do scientists actually detect these fleeting interactions?
Well, the main way we detect positronium is by analyzing that characteristic annihilation radiation we talked about. As we said, PPs gives you two back-to-back 511 keV photons. OPs, on the other hand, gives you three photons, and their energy adds up to the same total. But individually, they have a continuous energy spectrum. It's these distinct signatures we hunt for.
Right. And I imagine you need some pretty specialized detectors to capture and tell apart these light signals, especially given how fast it all happens.
Indeed, yes. We use highly sensitive scintillation detectors, things like sodium iodide crystals, sometimes doped with thallium, or bismuth germanate crystals. These materials basically convert the energy of an incoming photon into a tiny flash of light.
Scintillation. Yeah.
And by arranging multiple detectors, often in a ring around the sample, we can measure not just the energy and the angle these photons come out at, but also the precise time differences between when they hit the detectors. This complex setup is what lets us distinguish the two-photon decay of PPs from the three-photon decay of OPs. It's really a testament to the precision of modern experimental physics.
And for actually measuring those incredibly short lifetimes, I gather there's a specific, quite powerful technique.
Absolutely. It's called positron lifetime spectroscopy, or PALS. That's a key method. It works by measuring the time difference between the moment a positron enters the material, usually signaled by another gamma ray from the radioactive source, and the subsequent detection of its annihilation photons.
Ah, timing the whole event.
Exactly. By plotting these time differences for many, many events, we build up an exponential decay curve. And the slope of that curve tells us the average lifetime of positronium in that specific environment. This technique is remarkably sensitive. It lets us figure out the relative amounts of ortho and parapositronium, and importantly, infer details about the material it's interacting with.
It's pretty amazing how the way it dies, how long it lives, tells us so much about where it lived, even for that tiny fraction of a second. But this isn't just about fundamental quantum physics, is it? Where does positronium actually step out of the pure research lab and into, well, real-world applications?
That's a really important point. Beyond the fundamental physics questions, positronium has found some very practical uses. It acts as a highly sensitive nanoscale probe for looking inside materials. Because its lifetime is so strongly affected by the electrons it encounters in a material, it tells us a lot about the material's properties, especially things like porosity or tiny defects.
So what does that mean for us practically? How does studying positronium actually help in developing or checking real-world materials? What problems does it solve?
Well, it gives us this unprecedented, non-destructive way to peek into the sub-nanometer world inside materials. It can reveal hidden defects or structures that, honestly, traditional methods just can't see. And that kind of precision is absolutely game-changing for industries like, say, microchip manufacturing or developing advanced polymers.
How so? Like with porous materials?
Yeah, exactly. In porous materials, like some plastics or ceramics, positronium can find tiny empty spaces, voids, and it can actually live longer inside those voids before annihilating. So by measuring that longer lifetime using PALS, scientists can figure out the size and distribution of these pores with incredible accuracy. That's crucial in fields like semiconductor research or polymer science, where even microscopic voids can drastically affect how the material performs.
And it's also a powerful tool for finding defects, not just pores, right?
Precisely. Positronium is a fantastic non-destructive tool for analyzing defects in solids. If positronium forms in places where atoms are missing lattice vacancies or in the spaces between atoms, its decay characteristics change in a very specific, measurable way.
Ah, so the fingerprint changes.
Exactly. By combining PALS with another technique called Doppler broadening spectroscopy, or DBS, which looks at the energy spread of the annihilation photons, researchers can identify these vacancy-type defects in metals and semiconductors. They can even quantify how many defects there are. For instance, ensuring the quality of thin films and microchips, where even atomic scale flaws can cause failure, really relies on techniques like this.
It really seems like we're just scratching the surface here. Looking ahead, where do you see the most exciting, maybe even revolutionary future applications for positronium?
For me, the truly exciting, really forward-looking potential lies in quantum information technology, its unique quantum properties, especially its natural ability to form entangled states. That makes it a remarkably promising candidate for future quantum computers and quantum communication systems.
Okay, using something that vanishes so quickly to build quantum computers sounds, well, counterintuitive. What makes it a good fit for creating qubits, the basic units of quantum computing?
The absolute key is its inherent entanglement. As a system made of an electron and a positron, their quantum properties, specifically their spins, can be intrinsically linked or entangled. Positronium, for example, when it decays into two photons. Those two photons are naturally spin entangled.
Ah, okay.
So positronium is like a ready-made source of entangled particles, and entanglement is the fundamental resource for quantum computing. You could potentially use these entangled states to define the logical eries and ones of qubits, maybe manipulate them with magnetic fields acting on multiple positronium atoms, or perhaps using precisely controlled laser pulses. It's like having a natural factory for entangled pairs.
But that incredibly short lifespan, that still feels like a massive hurdle for any kind of sustained quantum computation or communication. How are researchers even beginning to tackle that problem?
It absolutely is a huge challenge, no question. Direct, long-term storage is incredibly difficult. But researchers are exploring some really ingenious solutions. One idea is trapping positronium inside nanoporous materials, materials with incredibly tiny pores. That can actually extend its lifetime, maybe by an order of magnitude.
Okay, trapping helps a bit.
A more promising avenue, perhaps, is using lasers to excite positronium into highly energetic states called Rydberg states. In these Rydberg states, the electron and positron are much, much further apart. This drastically reduces the probability that they'll annihilate immediately, and so it extends their coherence times, how long they maintain their quantum state. It's a remarkable bit of quantum engineering, really pushing the boundaries.
This brings up another important point. Can positronium actually help us test the fundamental rules of entanglement itself, like verifying Bell's inequalities?
Yes, it's an ideal platform for exactly that. Positronium gives us an unparalleled system for testing Bell's inequalities. These tests are crucial for proving that quantum entanglement is real, and that the world isn't just governed by hidden classical rules. The two photons from PP's decay are highly correlated, they're entangled, so scientists can measure their properties, like polarization, at different angles. Then they compare the results with what classical physics would predict versus what quantum mechanics predicts. And so far, the results have consistently backed quantum mechanics, validating our understanding of entanglement and really pushing the precision limits of these fundamental tests.
It really feels like we're using this strange little particle to peek behind the curtain of reality itself. And beyond quantum tech, you mentioned positronium seems to hold clues to some huge cosmic mysteries, particularly around antimatter and gravity.
That's a profound observation, absolutely. One of the biggest open questions in physics is, does antimatter fall down or fall up? Does it behave exactly like matter under gravity? Our standard model says there should be no difference. But some alternative theories suggest otherwise, which would completely shake up our understanding of the universe.
Right.
Positronium, being electrically neutral and made of both matter and antimatter, is just a perfect system to test this. Imagine generating a beam of positronium atoms in a vacuum chamber, and then measuring incredibly precisely how its path bends in Earth's gravitational field. Then compare that to a regular matter atom beam. The results could be truly revolutionary.
And connecting that to the bigger picture, if antimatter interacts differently with gravity, that could point towards completely new physics, right? What might that imply?
Indeed. A difference in how positronium interacts with gravity could potentially start to unravel the mystery of why our universe seems to be made almost entirely of matter, with very little antimatter around. It might hint that the fundamental laws aren't perfectly symmetrical between matter and antimatter, maybe leading to matter winning out after the Big Bang instead of everything just annihilating into pure energy.
Yeah.
That would fundamentally rewrite our cosmic history.
Wow.
Furthermore, positronium is also an unparalleled system for testing another fundamental symmetry, CPT symmetry. That stands for charge, parity, and time. This symmetry basically states that the laws of physics should look the same if you simultaneously flip the charges of all particles, view everything in a mirror, parity, and run time backwards.
A very fundamental concept.
Extremely fundamental. A violation here would unequivocally point to entirely new physics beyond the standard model. And because positronium doesn't have a heavy nucleus, it avoids all the messy complications from the strong nuclear force. This makes it an exquisitely clean system for CPT tests. We do these tests by making incredibly precise measurements of its energy levels, specifically the fine structure and hyperfine structure, which are tiny energy splittings caused by relativistic effects and spin interactions. So far, experiments show excellent agreement with CPT symmetry, but we're always pushing for higher and higher precision. Any tiny discrepancy could be huge.
And it also helps us nail down the values of fundamental constants and really put our best theories through their paces, correct?
Absolutely. Positronium spectroscopy, studying the light it emits or absorbs, allows for extremely precise measurements of things like the Rydberg constant, a fundamental constant related to atomic energy levels. It also offers incredibly rigorous tests of quantum electrodynamics, QED. Now, QED is currently our most accurately tested physical theory. But even minuscule deviations found in experiments looking at, say, positronium's Lamb shift, a tiny energy shift predicted by QED or its hyperfine structure, could hint at unknown effects, perhaps new particles or forces, pointing us toward the next frontier in physics.
It's just incredible how this one exotic particle helps us probe the most fundamental laws of nature and the cosmos. But amazingly, it also has this surprisingly practical side, even touching our everyday lives, you mentioned, in unexpected ways.
It does, yes. While all the deep physics is fascinating, positronium also plays a vital, if somewhat behind-the-scenes, role in a common medical diagnostic tool, positron emission tomography, or PT scans.
PET scans, right.
In PET, doctors inject a patient with a tracer molecule tagged with a radioactive isotope that emits positrons. These positrons travel a very short distance in the body's tissue before they inevitably encounter an electron and annihilate. This annihilation produces two of those characteristic 511 keV photons going in opposite directions, which are then detected by the PT scanner to create an image.
Okay, but where does positronium fit in?
Well, it turns out that positronium can actually form as an intermediate step before the annihilation happens inside the tissue. And interestingly, the lifetime of this positronium atom before it annihilates is subtly influenced by the local chemical environment, the types of molecules, and the structure of the biological tissue right where it formed.
So it's not just a background effect in PET scans, it's actually a potential diagnostic opportunity itself.
Precisely. Researchers are exploring whether analyzing the lifetime of positronium formed during a PET scan could give us extra information. Could we, perhaps, differentiate between healthy tissue and cancerous tissue based on subtle differences in positronium lifetime? Or study metabolic processes at a molecular level with even greater sensitivity? It could significantly enhance the diagnostic power of PET, potentially leading to earlier detection of diseases like Alzheimer's or specific cancers, maybe even mapping things like oxygen concentration in tissues, giving a much clearer picture of tissue health. It's an active area of research.
That's fascinating. Looking even further into the future, what are some of the more speculative, maybe, but genuinely exciting possibilities for positronium technology that people are exploring?
Well, the ability of positronium to reliably produce entangled photons makes it a really strong candidate for future advanced quantum communication systems. Think about quantum cryptography for completely unhackable data transmission, or maybe even steps towards quantum teleportation, transmitting quantum states over distances.
Quantum teleportation.
Yeah.
Wow.
Beyond that, researchers are exploring truly exotic states of matter involving positronium, like positronium molecules Poisson 2-2s, where two whole positronium atoms actually bond together. Or even trying to create Bose-Einstein condensates made entirely of positronium atoms. This is a state of matter where all the atoms hack like one single quantum wave. Achieving that could reveal entirely new physical phenomena, things unlike anything we've ever seen before.
The scale of these potential future applications, from secure communication to entirely new states of matter, it's genuinely staggering. Even with those big challenges of stabilizing and controlling positronium, the potential for really revolutionary discoveries seems immense. What a journey we've been on. From its fleeting existence as this electron-positron pair to its profound implications for quantum computing, antimatter research, even down to medical imaging, positronium truly is a remarkable system.
It really is a perfect example, isn't it? How the smallest, most ephemeral components of our universe can hold the keys to answering some of the biggest questions. Positronium just keeps pushing the boundaries of our understanding. Quantum mechanics, QED, fundamental symmetries. It touches everything.
Indeed, it challenges our assumptions, it gives us new tools for science, and it definitely offers a glimpse into a future that could be shaped by quantum technology. We've certainly learned a huge amount from Yorgo Schneppat's insightful essay on this incredible subject.
And the research just keeps going. Every new measurement, every refined experiment holds the potential for a deeper understanding, or maybe even an entirely new discovery we haven't even thought of yet.
So what kind of new physics or perhaps groundbreaking technology will positronium unlock next? That really is a question for you to ponder. We really hope you've enjoyed this deep dive. If you'd like to explore more, you can find further information over at schneppat.de. Thanks so much for joining us, and we'll catch you on the next deep dive.